Dieback and gloss loss after bake are two of the most perplexing defects for solvent-borne automotive coatings because the film often appears perfect immediately after application and even after flash-off. Yet visual and instrumental inspection after oven curing reveals reduced gloss, haze, or uneven reflection. From an OEM RD&I standpoint, these defects are not indicative of poor formulation alone, but are the optical consequence of subtle interactions between solvent evaporation, film formation, and cross-linking kinetics. Understanding these phenomena requires evaluating not just chemistry, but the complete process window from application through final bake. Visually, dieback manifests as areas where the surface appears slightly duller or lighter than surrounding regions, sometimes showing a washed-out look in localized zones. Gloss loss is measured instrumentally using 20 degrees, 60 degrees, or 85 degrees geometries and may be uneven across panel edges, corners, or horizontal surfaces. Unlike orange peel, which is a topography issue, dieback and post-bake gloss loss occur even on a visually smooth surface. Under magnification, subtle surface micro-roughness, reduced clarity of reflection, and minor texture variations are often apparent. These defects are often more noticeable under directional side lighting, which exaggerates changes in light scattering. The root causes are multifactorial. Residual solvents trapped beneath a partially cured surface can reflow or migrate during bake, disturbing pigment orientation and modifying the surface microstructure. This is particularly pronounced in high solids coatings with a complex mixture of fast and slow solvents. Film thickness sensitivity is critical. Excessively thick DFT increases diffusion path length for tail solvents, which cannot escape efficiently before crosslink density rises. The resulting uneven solvent release leads to local variations in refractive index, producing a loss of gloss. Conversely, thin films may appear uniform but may fail to achieve full cross-link density, contributing to subtle haze or clarity loss. Flash-off and temperature profile are key process variables. Insufficient flash-off traps solvent in the lower layers of the film, creating a semi-elastic surface that cannot maintain pigment alignment during oven ramp. Too rapid an oven ramp generates internal stress gradients, causing pigment and binder redistribution that reduces specular reflection. Controlled flash-off ensures the surface has enough mobility to allow tail solvents to diffuse outward gradually, while the oven ramp builds modulus in harmony with solvent escape. Solvent balance within the formulation is another critical factor. Fast evaporating solvents leave the surface too quickly, causing early skin formation, while slow tail solvents trapped beneath may create microcavities and localized surface tension differences. Both scenarios can lead to post-bake gloss anomalies. In hot ambient conditions, this effect is amplified, and the same formulation that performed perfectly in cooler labs may fail in production. OEM plants often simulate this with accelerated environmental trials to refine solvent blends before full-scale production. Viscosity and flow behavior further influence dieback and gloss loss. High viscosity systems may resist surface flow, locking pigments into irregular microtopography, while low viscosity systems may sag, introducing subtle surface waves. Both can affect the final light scattering properties without causing visible orange peel. Rheology modifiers can improve pigment orientation and surface leveling during the critical flash-off window, but overuse can stiffen the film prematurely, limiting pigment mobility and exacerbating gloss issues. Additives play a supporting role. Surface active agents can improve wetting and pigment dispersion, reducing localized refractive index variations. Flow and leveling additives optimize micro-smoothness, enhancing gloss recovery post-bake. However, additives cannot compensate for fundamental process errors, such as excessive DFT, insufficient flash-off, or overly aggressive oven ramps. OEM RD&I practice emphasizes that additives are fine-tuning tools, not corrective fixes for dieback caused by poor process control. Once gloss loss or dieback appears post-bake, corrective options are limited. Minor haze may be improved through polishing or post-cure buffing, but localized dieback caused by solvent entrapment or pigment misalignment requires removal of the coating and reapplication under corrected process parameters. This is why OEM plants focus heavily on process validation. Controlled DFT, accurate flash-off timing, precise oven ramp, and proper ambient conditions for every batch. The diagnostic strategy involves measuring gloss across multiple angles and comparing it with visual inspection to identify zones of dieback. Correlating these areas with DFT mapping, flash-off logs, and oven temperature data allows OEM teams to pinpoint root causes. Once the mechanism is identified, whether solvent migration, pigment misalignment, or insufficient modulus development, process adjustments can be made systematically, reducing trial and error and rework. The key takeaway is that dieback and post-bake gloss loss are not random failures. They are the optical signature of how the coating behaves during solvent release and early cure. Treating these defects purely as chemistry issues without analyzing process variables will never produce consistent results. By controlling flash-off, DFT, solvent balance, viscosity, and oven profiles, OEM plants can achieve both uniform appearance and durable performance consistently. If you're experiencing dieback or gloss inconsistencies after bake, or if gloss recovery seems impossible despite correct formulation, leave your questions in the comments. Future episodes will analyze real OEM plant cases and show the exact corrective steps applied to eliminate post-bake dieback permanently.